Hello, everyone, and welcome back to Introduction to Logic. This week, we're going to be continuing with modern logic, this time with natural deduction. So we're going to be leaving truth tables behind to replace it with something that's a bit more nuanced. Right? A truth table is really like a brute force way of checking all the possible truth values for an argument, right? That way you can measure its validity. But there are certain limitations to truth tables. So the reason why we want to use natural deduction or proofs is because truth tables can be really cumbersome, right? We already know that if you have three sentence letters, right? Let's say P, Q, R, you're looking at 8 rows for your truth table. Increase the number of sentence letters to 4, and you're looking at 16, right? So they can get really long really quickly, right? Some arguments you want to consider might have 10 sentence letters. And that's not a truth table that you're going to want to do yourself, right? That's not something you want to actually write out on paper. So what natural deduction allows us to do is to simplify this process. Basically, the way it works is that it allows us to use rules of inference, so things that we know to preserve validity, to transform some propositions into others, or to allow us to make inferences from some propositions into others. A lot of this is really basic. Some of it you probably know just intuitively. For example, we've seen if P, then Q before, right? If P, then Q. Well, if you also know that P is true, what do you think you can derive? Well, you can derive Q from that, right? If premise 1 is true and premise 2 is true, the conclusion has to follow. This is called modus ponens, right? This is modus ponens, and we can use this as an inference rule whenever we see a conditional, right? So if you see something like if A, then B, and you know that A is true, well, guess what has to be true? B. And we know that because of modus ponens. So these inference rules that we're going to learn are going to allow us to transform things like these premises into conclusions while preserving validity. The idea being, if you can show that your premises allow you to produce the conclusion using only valid inference rules, you have proven that the argument is valid. Okay? All right. But first, we need to learn the rules, right? So what are the rules of natural deduction? Well, in general, there are like 5 or 6 main rules that every system uses. Now, when I say system, I mean the sort of terminology, the moves that your book or instructor wants to use. We're going to be using the one within our textbook, which again you can find in the description of this video. But there are many other systems out there. They're not all going to look quite like this. However, these are pretty good general rules. Within this system, for all x, most inference rules have an introduction and an elimination rule for every connective. You know, our connectives are conjunction, disjunction, we have negation, conditional, and biconditional. So you can expect there to be an introduction and an elimination rule for each one of these. An introduction rule, right, so intro, is going to end up adding one of these symbols, right? Whatever we do using that rule, we're adding one of those symbols. Whereas an elimination rule, or elim for short, is going to take one of these symbols away. This will make more sense as we get into things. First, we're going to begin with one of the exceptions, right? So our first rule is not introduction or elimination. It's simply called reiteration. Reiteration. Now, reiteration allows us to derive a thing we already know. Okay. So if you know P, for example, well, you can conclude P. How? Well, you cite reiteration, or just reit is fine, and the line that it came from. And that's it, right? So reiteration is a very simple move. It's basically just repeating something you already know or are assuming to be true. All right. More general notes about proofs. There's a certain way in which we're going to be doing them in this system. Every time you want to prove something, let's say we do want to prove that from a premise P, you can get to the conclusion P. This is what it would look like. You're going to start with a vertical line. Okay? Start with a vertical line, and then a horizontal line perpendicular to it. We are going to put our premise above that horizontal line. Okay? And go ahead and label it 1. Step 1. What this horizontal line is doing is saying, I'm assuming everything above this line. Horizontal lines in this system indicate assumptions. So I'm assuming my premise, P, is true. Remember, just because an argument's valid doesn't mean that the premises are actually true. We have to assume that they're true to test validity. So let's assume it by putting it above that horizontal bar. Everything below a horizontal bar that's within the same scope of the vertical bar here is a product of that assumption. So on line 2, I can say P, citing reiteration, line 1. And that's it. I don't have to do anything else for this proof. I have shown that by assuming P, right, my horizontal bar here marks an assumption of the premises, I can derive P. Notice how my deriving of P is now under the assumption. That's what we're looking for. So this shows us, yeah, that's valid. This argument is valid. It's not a very interesting argument, right? I can prove to you that P if we assume that P. Great, okay. That's not super interesting, but it's a way to get us started. Now, you don't have to cite anything here. Why? Because it's an assumption. It's an assumption of our premise. See, this bar tells you everything you need to know. Anything above this is an assumption, and therefore there's no rule to cite. If it helps you, you can write premise here, right? If that makes things clearer for you, you can do that, but it's not strictly speaking necessary. Now, this citation, however, is critically important. If you declare something to be the case that does not have a horizontal bar under it, that means you think it's not just an assumption. You think you can get it using a valid inference rule. You need to prove that that's the case, and so you have to cite first the rule that you're using. Here we're using reiteration. And second, the line number that it relies upon. So this relies upon step 1, right? Okay, so that's how the arguments are going to look as we build them. That's reiteration. There's really nothing more to say for it. It's very simple, but you will see later that it does have its uses. It's not always going to be used for uninteresting insights. Sometimes we really do need it in order to move forward in a more complicated argument. Okay, so next up, we're going to look at our conjunction rules. And this time, they really do have an introduction and an elimination version. So let's start with conjunction introduction. Conjunction introduction. We know that if a conjunction is true, right? If a conjunction is true, both sides of it have to be true, right? Well, the reverse holds as well. So if I know that P is true, and I know that Q is true, well, it follows that I know that the conjunction between the two is true. Okay? That's all conjunction introduction is going to do for us. Simply put, it says you can combine any two lines together with a conjunction sign, no matter how complicated those lines are. So let's look at a couple examples. Let's give the one we just wrote here, but let's also look at something more complicated. Let's say if P then Q and R, and I want to prove if P then Q and R. So let's do both of these. We're going to start with our vertical line, then our horizontal line. Okay. And we're going to write our premises above this vertical line. So we have P and we have Q. That's 1 and that's 2. Conjunction introduction says if you have two things, you can combine them with a conjunction sign. You can introduce a conjunction symbol. So we're going to do that. P and Q, conjunction introduction. You can just write the conjunction symbol with an I. And here you need to cite both lines that you're combining. So that's 1, 2. And that's it. Conjunction introduction. Let's do the second proof. Or the second argument, rather. Here we go. Premise 1. If P, then Q. Premise 2 is R. We're going to do the exact same thing, right? It doesn't matter how complicated a line is, you can always combine it with another one so long as you put a conjunction symbol between them. Okay? So, if P, then Q and R. And once again, conjunction introduction, 1, 2. Okay? Now, conjunction is symmetrical, which means that this, P and Q, means the same thing as this, Q and P. There is no difference in terms of their truth values. However, when we're making proofs, it's important that you do things in the right order, right? So you should write 1, 2 here instead of 2, 1, right? Just technically speaking. However, you could have written this. You could have derived R and if P, then Q. Okay? And this would be conjunction introduction 2, 1. See? So conjunction introduction, once again, just combines any two lines with a conjunction symbol in between them. Okay? Fairly simple. Now let's look at conjunction elimination. Okay? Conjunction elimination. Conjunction elimination says that if you have a conjunction, you can break it apart. So if I know that P and Q is true, well, I know that P is true too, right? So you are eliminating the conjunction symbol. Here's how that works. So premise 1, we need to move this. Premise 1, P and Q. Okay? I can derive P from that. That's conjunction elimination from line 1. I can also derive Q from that. conjunction elimination, line 1. You can take the left or the right side. It's up to you. Okay? And once I have done this, once I have gotten P and Q by themselves, I can combine them back together again in a different order with conjunction introduction. 3, 2. See? So, conjunction rules are fairly simple. You can either bring any two lines together with a conjunction symbol in between them, or you can take any existing conjunction apart into their more base elements. More technicalities about conjunction elimination. You can only do this if conjunction is the main connective. So if you have something like this, for example, it's not the case that P and Q. You cannot use conjunction elimination here. Why? Well, it's because this is a negation. It's not a conjunction, right? You can only use conjunction elimination if it is the main connective. Similarly, if you had something like if P, then Q and R, you cannot do anything with that conjunction because the main connective is a conditional. You should be looking at conditional rules, not conjunction rules. Okay? All right. Now, these three rules are fairly simple. Reiteration, conjunction introduction, conjunction elimination. They're fairly simple. Most people get them pretty quickly, right? The next rules we're going to discuss can be a little trickier. Okay, so we're going to now start with our conditional rules. So first up, we're going to do conditional elimination. Conditional elimination should be very familiar to you now. In fact, we led this lecture with a conditional elimination. It says that if you have a conditional, like this, if P then Q, and on another line, or another premise, you have the antecedent, which remember is the left side of a conditional, you can always derive the right side. Okay? So this is conditional elimination. Again, we are getting rid of a conditional. So another way to think of conditional elimination is that the left side can unlock the right side. The left side can unlock the right side. If you have the left side like this, you can unlock the right side of a conditional. All right. So you can think of a conditional like a keyhole, right? The conditional is a keyhole, and the left side of it is a key. If you have that key, you can open the door and get what's behind it. That's conditional elimination. All right, so now we can start to build these things together. Let's say you have something like this. Premise 1, P and Q. Premise 2, if P, then R. Okay? Conclusion, R. We have enough tools now that we can actually prove this. So let's do so. We get our vertical bar first. Then we need a horizontal bar indicating our premises have been assumed. Premise 1, P and Q. Premise 2, if P, then R. And we're trying to get to R. Okay? We're trying to derive R. Well, I notice that R is here in my premises and that it's behind a conditional. So I know that I need to somehow get the left side of that conditional free. Well, as it would happen, I have the left side of the conditional in a conjunction, and I know that when I have a conjunction, I can break it apart, right? That's and elimination from line 1. Now that I have it by itself, I can get R using conditional elimination. And here's the thing, always cite the line with a conditional on it first. So 2, 3. Okay? 2 and 3. You cite the line with the conditional first. Here. And the second thing you cite is the line that has the left side of that conditional, that has the key. Okay? Simple as that. So conditional elimination is not so bad. Conditional introduction is its own kind of beast, okay? It's going to require that we make assumptions. So conditional introduction basically tells us that if you can assume something and derive a result from it, you are entitled to establishing a conditional relationship between those two things. So, for example, if I assumed P, okay, if I assumed P, and I was able, through some process of valid inferences, to arrive at R, then it would be acceptable for me to conclude that if P, then R. Okay? That would be acceptable. So, let's look at an example to see how this would work. Let's get our vertical bar first. Okay. And let's say you know that if P, then Q, and if Q, then R. These are your two premises. Let's write it out in argument form. If P, then Q, if Q, then R, and I want to derive if P, then R. Okay? That's what I'm looking for. So we have our premises here now. Okay. So when your conclusion is a conditional, not always, but quite a lot of the time, you're going to need to do conditional introduction because you're trying to introduce a new conditional, right? This won't always be true. There are some exceptions, but quite a lot of the time it will be true. The way you do conditional introduction is you begin by assuming the left side. You assume the left side of what you're trying to prove. So I'm going to assume P. Okay? But I need to make it clear that this is an assumption. It's not something I'm actually entitled to. That's going to require me to draw another series of lines. Bear with me. There we go. Again, the horizontal line underneath the P indicates that what is above this, what is immediately above this line, is an assumption, and what is below it is coming from this assumption. The vertical bar indicates the range of that assumption. You'll see what I mean as we go on with this proof. So, step 4, now that I've assumed P, I can get Q. Well, how do I do that? It's by using conditional elimination, right? If you look on premise 1, I have if P then Q. Well, I just assumed that P is true, so now that entitles me to derive Q. That's going to be conditional elimination 1, 3. So why am I entitled to get Q given that this P is an assumption, right? This is an assumption, so do I actually know it? This is where the vertical bars come in. Notice that P here is still under this vertical bar all the way on the left. That means that I am entitled to use this information, right? Okay, so P still falls under those assumptions. I can refer to any information that's either within the same level of vertical bar or to the left of it, right? Okay. Again, more practice will help make this clearer. Step 5, I now know Q. Well, I can now derive R using the same move, conditional elimination from lines 2 and 4. Notice here I have if Q then R on line 2, and on line 4 I have Q. Okay. Now I get to do the conditional introduction step. On line 6, I can say if P, then R, conditional introduction 3 through 5. Now let's walk through why things are as they are on line 6. First thing to note, I am no longer under the vertical bar here that I was when I assumed P. What this means is that I have terminated the assumption. I've closed it. I'm no longer under this assumption of P. If P then R is not dependent on any assumption other than the premises. It's just true if the premises are true, okay? So I get to leave the assumption. There's only a few ways you can leave an assumption, and one of them is conditional introduction. That's the only rule right now we have for terminating any assumption, okay? So I'm allowed to come out one level of assumption. Second thing, 3 through 5. Notice I'm not using a comma this time. The way you cite conditional introduction is the entire subproof that you use to get to the new conditional. In this case, it started on line 3 and it ran all the way down to 5. So just look for the top of that subproof vertical bar and the bottom of that subproof vertical bar. And it's that through that, right? Simple as that. Now that I have if P then R, can I just derive R, right? Can I just do this? Conditional elimination 6, that's where my conditional is, 3. See? I have a conditional here, and it seems like I have the left side of it here. No, you can't do this. This is an illegal move, right? It is an invalid inference. Why is it an invalid inference when it looks like it has the same pattern? Well, it's because P, this P, is assumed, and I'm no longer under that assumption, which means I no longer am entitled to that information. See, now that I've left this vertical bar, I'm to the left of it. I cannot refer back to it, okay? That's why the vertical bars are so important. They help you keep track of what information you can and cannot refer to. And you can't go right. You cannot refer to information that is further to the right of the vertical bar you're presently under. Okay? So line 7, you can't do that. But in terms of proving the validity for this argument, we did it. All right? Check. We proved that it was valid. Okay, so those are all the rules that we're going to learn this week. It's best to get them kind of a little bit at a time so you're not completely overwhelmed by them. But we can try a couple more examples here. Suppose we know that if P and Q, then R. Okay? And we know that if S, then P and Q. All right. Further, we want to know, or we want to prove, rather, that if S, then R and P. Okay? We want to prove that this is the case. There we go. How are we going to do that? Well, we're going to start the same way as always with a vertical bar and then a horizontal bar for our premises. Premise 1, if P and Q, then R. Premise 2, if S, then P and Q. Let's give them numbers, 1 and 2. Now, first thing I notice, the conclusion I'm trying to derive is a conditional. So I'm very likely going to need to start with an assumption for the sake of a conditional introduction. How do I do that? I'm going to start by assuming the left side. So I'm going to assume S on line 3. Now I need bars to indicate that this is indeed an assumption. Left bar, and then we need the horizontal bar. Okay. On line 4, I'm going to see if I can use that assumption to get anything useful. It looks like I can use it in combination with line 2 to unlock P and Q, right? That's conditional elimination, line 2 and 3. But what I'm trying to get is R and P, not P and Q, okay? So this hasn't been completely what I'm looking for. I need R. I need to get R somehow. Well, if you notice, P and Q is the key to unlocking R from line 1. So I'm going to get R now using conditional elimination 1, 4. Now I just need to get R and P. That's going to require me to break apart the conjunction on line 4. I just want P. I don't care about Q. So I'm going to get P by itself using conjunction elimination, line 4. Now I can bring the two back together. I can say R and P using conjunction introduction, line 5, 6. Okay, perfect. That's exactly what I was looking for. Which means on line 8, I can come out of my assumption and write if S, then R and P. Conditional introduction 3 through 7. And I proved it's valid. Okay? I didn't require a truth table, but nevertheless, this is 100% valid because I only used valid inference rules. Okay? Now, the last example I'll show you is a fairly simple one, but I think it's important so that you know you're not always, when you see a conditional as your conclusion, going to be using conditional introduction. Say you have something like A and if B, then C. Okay? And you want to know if B, then C. Pretty simple, right? It's only going to require one step. Premise A and if B, then C. That's premise 1. And step 2, if B, then C, conjunction elimination 1. So just because you have a conditional as your conclusion, it doesn't necessarily follow that you're always going to be using conditional introduction. What I would say is a matter of general advice where deciding whether you need conditional introduction or not goes. I would say look at your conditional. If you have a conditional as a conclusion, see if you can find it anywhere in the premises. If it appears as some element of a premise, then you might not need to use conditional introduction. But if it does not appear, the entire conditional, if the entire conditional does not appear anywhere as an element of a premise, you very, very likely will need to use conditional introduction. Again, there might be some minor exceptions, but that's a good general rule. Okay, so keeping it pretty simple this week with only these 5 rules. Next week, we're going to look at a few more complicated rules. But that's going to be it for now. So I'll see you next week.